we can start. So, welcome. It's been a week since we last looked at Neo4j Bloom, and today I wanted to explore one of the fun datasets that I really like, which is Stack Overflow. You all probably know Stack Overflow, which is the place where we all go to answer and ask questions. By the way, my only question on Stack Overflow that I ever asked in my whole life was a really silly April Fool's joke, which was this one. Why did Neo4j change its name to Neo4j 5J, Neo5J? So anyway, that was the only question I ever asked on Stack Overflow, but I answered like thousands. So it's a fun data set. If you know Stack Overflow, then you know that you have things like the question, the person asking the question, votes, up votes, down votes, tags, and answers by more people. And what we want to look at today is kind of how can we get this Stack Overflow data into Neo4j, and what can we do with that. So, for instance, for Neo4j, we have in total, I think, here can we see that almost 20,000 questions for us so far in the last 3 years. And some people who are very active in answering these questions, and all-time top answers as well. And you can already see that there are lots of tags in this database. And what's really cool is it also shows related tags, right? So to Neo4j, all these tags are related, and you see like how many co-occurrences do they have. So for instance, if I click on Pi2Neo, I see Pi2Neo as a tag is correlated to Neo4j and Python and Cypher and Flask and graph databases and so on, with kind of lower correlation here. And so that's some of the data we want to explore. And fortunately, Stack Overflow has an API that's super easy to use that you don't have to sign up for. And so that's what we're going to use. But of course, you also need a Neo4j database. So I thought I join you starting from scratch. Basically, creating a sandbox. So if you want to, you can come along. I just want to see, because I didn't set up my other computer, if there are any questions along the way. So I'll just put Twitch on my phone. Let's see if this works. So if you have questions, then I should see them on my phone as such. Cool. So we create a new sandbox project, and I want to use the graph data science sandbox, which has some data in there, which we're going to get rid of, but it comes with the graph data science library and Neo4j Bloom together, which is really nice. So we just launched this project. And while it's starting, it takes about 30 seconds or so. We can look at the Stack Overflow APIs and what we can do with that. So Stack Overflow has an API which is really nice, which can give you, for a given tag, in this case it's Neo4j, 100 questions per page. I order them here descending by creation date, so like the newest questions first. And then cite a Stack Overflow, so not like something else. And then you can page through this result. So it's like a JSON, and you see we have like the question, its tags, who posted these questions, all these counts that are on it, creation date, and so on, the content. And if the question has an answer, then there's a nested field for comments or answers, right? So here's one field for comments and one field for answers as well, right? So, and for the answers, we have again who kind of sent the answer, what's the content, and what's the link, and also what are the votes on this answer. So we can use APOC, my favorite utility library in Neo4j, to get this kind of data. By the way, if you want to look at larger data sets, you can also download the dump of Stack Overflow from Internet Archive, and then just use the Neo4j batch importer to import that. So I wrote a JavaScript that kind of takes their dump format, which is basically just an XML format, which is a little bit odd. It turns it into CSV, and then you can just use the batch importer to import it. So if you want to learn more, there's this blog post which explains this in more detail. Okay, but let's look at APOC. So now that the database should be started, we can open browser for this database. And we want to do two things. So first of all, we want to get rid of the data that's in there. I mean, it's a little bit sad because it's Game of Thrones data, but so be it. So there's a bunch of nodes and bunch of relationships, and we just get rid of these. Match n, detach, delete n. So it's not a large data set. So, and we also close the guide for graph data science. So if you're interested in more details about the graph analytics parts, feel free to restart a sandbox of this kind and get going with that. So we clean it out, and the other thing that we can clean out is the remaining indexes and constraints. I already have this here somewhere in my, is this here? Somewhere. I thought I had them. So we can basically just do call db.constraints, which gives us the constraints, and then we can just yield description and then return drop plus description plus semicolon. Which need to enable multi-statement editor in the browser, and then we can basically just take these and remove the equal signs, and then we are good to go. Oops. Of course, we didn't want to do this, but we want to do this. So then we are good to go with our database. So it's cleaned out now. We definitely want to provide an GDS and Bloom sandbox that is blank, but so far it's not there, so we just reuse this one. So this is now cleaned out, so there should be hopefully no things left here. Let's see. Yeah. Okay, cool. So, and this is what we want to use for getting our Stack Overflow data in. So I can look in the APOC docs, and APOC has an documentation on load.json. And in the load.json documentation, it has one section that says import from a Stack Overflow API, and that's what we're going to steal. So you already saw the API call that I showed you here in the browser, which just returns JSON. And then you can, of course, get this data back and then show what's in there, but you've already seen the JSON, so I can just quickly run this. And it shows us only all the questions, and for each question, the title, owner, creation date, and what other properties are there on the data. I forgot to copy the W. Okay, so it fetches the data and shows me what's the title, what's the owner, creation date, and what other keys are there. So cool. But fortunately, the APOC docs already provide us with a ready-made statement down here that creates a full graph, which is what we want to use today. So you can just copy that. Oh, by the way, if you want to find this, then you can just search for APOC docs Stack Overflow, and then you end up here on load.json chapter 5 import Neo4j. So that's kind of the quickest way to get there. Okay, so I just copied the statement, and now we can import this data. So it loads this stuff from the API, creates a question for each item, only copies a few of the attributes. So if you want to do more, you can also extend this, also add up and down votes and lots of other view counts and whatever. So you saw that there's a lot of attributes on each question here, like there's close vote count is answered, favorite count, view count, up and down votes, and so on. Here I only have the base attributes. And then for each tag, it merges, it creates the tag, if it doesn't exist already, and connects the question to the tag. And then for each answer, if there are any answers, then it connects the answer to the question, and also creates a user for the answerer. And if it doesn't exist, and then connects the user to the answer. I didn't do comments here, but if you wanted to, you could also do comments as well. And then because sometimes the owner is deleted from Stack Overflow, then it's actually null. Sorry. Two finger backwards on Chrome is not so much fun. So we need to copy to paste this in again. Because sometimes the owner is null, that I just filtered it out, and only if the owner is not null, we create also the owner of the question, so the original poster, and connect this to the question. Okay. And then we get our data. So this is page number one, but we can also iterate over multiple pages, but let's just create this one page of items. So you see it went really quickly and created a bunch of nodes, 400 nodes, and 500 relationships. So what we also want to do is probably create a constraint on the tag assert.name is unique, so that we don't get duplicate tags. And the same for questions. Q.question, and question ID should be unique. And then I also create index on question title, and we create an index on user display name. So it should be the display name, I think, at least. Display name, yeah. Okay. Cool. So we loaded our data, created a bunch of indexes, and which we don't really need as much, but because we want to look at the data in Bloom later, and Bloom uses the indexes to quickly look up and use and so on. And so we can look at our data model. We can say call db.schema.visualization, which is the same as epoch metagraph, basically. And here we see this is our little schema, and it has a user who asked a question or provided an answer, as we saw in the status statement, and an answer which answers the question, and a tag which kind of combines questions into categories or groups. Cool. So that means we have some data in here. But currently it's not so much. So what I want to show you as well is how we can multiply this. So this was like page one. So what we can do is we can just unwind over a range, unwind range 2 to 10, let's say 10 pages as page. And then we just append an ampersand page equals plus page here, and then it should pull pages 2 to 10 into the graph as well. Okay. Let's see. Otherwise, my phone doesn't like to chat. Or does it? So we can run this, and it will load the 10 pages. So let me just quickly check the Twitch chat on the computer so that I don't miss any questions from you guys. Come on. Or yeah. Okay. Cool. So it has one issue where it has a null ID. So I probably guess that's a deleted answer or a deleted question. That's interesting. So if I remove the answers here, let me run this again and see if it works. Yeah. So we don't really need the answers for everything, so that's fine as well. Actually, it would be kind of nice to also have the answers. What we can do is we can filter out only answers that have an ID, where q.answers in where not a.ab is now. So let's try this again. So these are only answers that have an ID. And I hope that the users of the answers are not deleted. Otherwise, you need to. Okay. So it did something. In q.answers, where not a.id is now. It has an ID, right? Or no, it's answer ID, sorry. No, then it caps the user down here. And not a owner dot user ID is now. I really don't like that they just replace the stuff with now. Okay, so now we get also all the answers except for this one user who got deleted or deleted themselves. Okay, so now we have some more data in our graph, 3,000 nodes, 5,000 relationships, which is nice. And now we can start to explore our graph. So for instance, what we can do is to reproduce like the top users thing. So for instance, I can say, okay, let me find users who ask questions. And then we just return the display name and number of questions that they are asked, order by frequency, descending limit 10. So usually I would not aggregate on display name because that's not very efficient. I would just aggregate on U. So that's actually proper cipher. Let's do it properly. And you can also do the limit first and then only return the remaining results. So we only need property access for the things that we actually return, so which makes it much faster. So we see Bruno, aerodynamica, SecTech guy were the ones that asked the most questions in the last few weeks, which is like the 10 pages that we've seen. But what's more interesting is kind of how many people answered questions. So people providing answers. And here we see Cybersam, Inverse Falcon, Dave Bennett. So Inverse Falcon is Andrew Bauman, Luan, Publicimo, and so on. And if you look at the top users here, you also see that this matches at least partially the things because they have different time frames. So they have 30 days and all time here, and we have something in between. So we could also do other fun things. So for instance, we can say, okay, how many questions are there per time frame? Return q dot. Did I store the created at? I'm just not sure. No, I didn't store the created at. But if you had stored the created at, we could have also said how many times questions per month or week or day or so were coming. So we can only look at the total questions in the time frame basically that we looked at 1,000 because it's 10 pages. Okay, so this is kind of a little bit playing around. Of course, you can do say something like people that provided answers to questions that were answers to questions that were tagged with a certain tag. So you now see like the beauty of graph queries. You can just continue that. That's actually 1, 2, 3, 4, 5, 6 joins in one line. And then we can say how many times did certain text come up, right? So for instance, if I want to look at, let's say, this user, where u dot display name equals this. So we want to see for this user the so we can also just simplify it for the time being. So for this user, we want to see kind of which text do they answer most frequently. So Neo4j, Cypher, of course, but then graph database, graph, Neo4j desktop, and so on. But if you look, for instance, at someone else like Publicimo, they have probably a different set of tags that they are answered, like load CSV is more in here, Neo4j client, which is .NET as such, right? Or the teacher, let's see what the teacher likes to answer. So you see also that different people have different preferences of what they answer. What's also interesting is you can look at the tags from other areas as well, of course, right? So if you want to import data, let's say from JavaScript or from Kubernetes or so, then you can just change the tag here in your query. Can even make this a parameter, and then you can also, of course, import also data from other things as well. So that's a little bit of exploration of the data. Of course, we can now in this sandbox, we have also Bloom built in, so we can just open our Bloom instance here. Or let's do the Bloom thing later. I just want to show you some graph analytics first, and then we can look into the Bloom thing. Okay, cool. So graph analytics. So what I want to do here is a little bit reproduce what I did back then with in this blog post here, Stack Overflow, which is correlation of tags in Stack Overflow. So this was the full Stack Overflow download, but I'm just doing this on the current one. So we have now the graph data science library on the Sandbox. So these are all the things that you can do with the graph data science library. So there's a ton of 133 procedures for all kinds of algorithms and management and all kinds of stuff. So what we want to do today is create an similarity graph between tags. So we want to basically identify how similar are two tags based on the co-occurrency on questions that they appear on. So for instance, if I click on Neo4j OGM, here in Stack Overflow, it shows me that it's related to Neo4j, it's related to itself, of course. So Spring Data Neo4j to Java, to Cypher, to Spring Boot, and so on, right? So, we want to see if we can reproduce this on our smaller data set, the similarity, right? So how similar are they? And not just by count, but also kind of how frequently did they overlap? So I want to have a similarity metric on that. Okay, so what we need for that is we have to project our graph into a compute graph. And we do this by calling GDS graph create. So GDS graph create. Oh no, let's start differently. So there's in the documentation for the graph data science library, there's one section on node similarity, which is what we want to look at, which is kind of the Jakarta similarity, which is computed by the putting the intersection of a number of comparisons by the union of a number of comparisons, right? So so kind of how many questions the two tags have in common versus all the questions for these two tags, and that gives you a similarity metric for these two tags. And so this is a built-in algorithm, and here in the documentation you see all kinds of configuration parameters for loading the graph, for projecting the graph, and so on. But if you scroll to the example, which is almost what you want to use here, It just says, let's create a graph and then let's just run similarity on top of that. And so we basically just steal this statement, but we just exchange, of course, our tags, so which is question here and tag. And then this would be tagged. So the similarity algorithm looks at the relationships in the inverse order. So I have to say have to provide the relationships in inverse order. So that's kind of the only thing that I had to figure out how to do. So so we have type as tagged for our relationship, and then orientation. It's not called direction, but orientation, which I also got wrong, is reverse, not inverse. That's also something I got wrong. So we are now get a little memory graph with 1,300 nodes and 2,800 relationships, which went really quickly, and it also shows you kind of what it pulled in for that in memory graph. So we can drop it again if you want to, but now we can actually call our similarity statement here. Let's just steal this one, which computes the node similarity between two tags. So we have to change our graph name because I called it tags. And we have two nodes here. I just changed this. I want to have the node as n1 and the node 2 as n2 because it only returns the IDs of these nodes as n2. And then I want to filter out. Actually, no, I don't need to do this. Let me see. Actually, we can tag 1, tag 2, tags. And then we limit 20. So this gives us the top n nodes in terms of similarity, and let's look at how similar they are. So so we see some things are very similar, so they appeared on the exactly same questions. It could be that there was only one question there, right? Or they were really super exactly the same. So that's a really high similarity. What we, if we remove the or increase the limit, let's say to 200, you see that it kind of starts at some point go down to smaller similarities as such, right? So Levenstein distance and eddy distance obviously also appeared on the same query, but then you see other similarities here as well. Right? And what you can do here is you configure this algorithm. Actually, let's do something else. We can also run just a stats version of this stats, which gives us just an overview statistic. So we see also what's the distribution of the similarity. So it basically compares these nodes, and then we get a distribution. So max similarity is 1, and then 75th percentile is 0.2, right? And it goes down to 25th percentile is less than 0.004, right? And here on the other side, you see what kind of configuration it uses by default. So degree cutoff is 1, so the node has to have at least one relationship. That's why it probably filtered out some of the nodes as well. And it also has a really minimal similarity cutoff. So that's why it would create quite a lot of similarity relationships because it's almost going down to 0. So what we could do is, for instance, we could say we want to have a similarity cutoff of, let's say, what did we see here? 75th percentile, 0.2. So if we run this again, then we see that the distribution changed because the 0.2 is now our lower bound here, right? So, and if you change the degree cutoff, so we say, okay, the nodes have to have at least, for instance, 2 relationships, then it changes again because then much fewer nodes have been taken into account, right? So let's run our algorithm with this and see how this changes the results. because I think the ones that we saw with 1.0 might not show up again because they might have only had one question. So here we see we have no ones anymore, but we have other things which are more interesting to look at. Right? So what's now cool with this is that we can actually turn this into a graph. So we can turn this into a graph which writes these similarities as relationships between our tags, which is what we want to do now. So to write the relationships, we need to provide a write property where the similarity is stored. So which we can call, for instance, wait. And we need a write relationship type, which we call similar. Right, and then if you run this, it should create similarity relationship. So it says it created 112 relationships on our graph. So which should show up here. Let's see if it refreshes. Come on. Ah, there. Can just steal the statement. It should actually refresh itself. Similar. So if you look at some of these relationships, then we see that they already form small clusters here, right? So you see stuff that goes together, ASP.NET, GrandStack, Apollo, GraphQL go together, PageRank and Directed Graph go together, Pythoneo and so on. Pythoneo with Python and so on. So this is quite nice. So we can look at this as an here's neighbor graph, because it also stores not all similarity relationship, but it has in top K, which is kind of the top 10 per node that are only written. So at most 10 relationships to other tags are written per tag, right? So it only takes the top K. So otherwise it gets a lot of noise as well of relationships that have very low similarity as well, which are not interesting for our KNN graph. So, and with that, we could actually start computing some other things. So for instance, we can say, okay, we have now these similarity relationships in there, and now we can look at creating a graph which has only text. So I just call this KNN graph. So it's a new graph in memory graph, which has only text and which uses the similar relationship, and orientation is undirected. So because I don't really care if A is similar to B is the same as B is similar to A, there is a difference, but this is more relevant for cosine similarities and so on. Okay. So let's see. If you create this graph, it should create a graph with these 159 nodes, 112 relationships. If I had more data in my graph, of course, this would be bigger. Let's see what happens. Yep. Oh, because it's undirected, it doubled the relationship count. Oh, it's more nodes, but it compared only 159 because that's kind of half of the amount. Okay, cool. So we have our similarity graph, and now we could run other algorithms on the similarity graph. So for instance, we can call something like weakly connected components. So we can do a call GDS, WCC stats, and provide a graph name KNN. And then tells me, okay, in this graph, we have a lot of different components, and most of these components are really small, right? So because they are, as you saw, due to my cutoff, it kind of isolated them pretty much already. So so there are not a large network of relationships, but it's really small clusters that are identified there. And if I wanted a full graph, then I would just reduce the similarity cutoff and the degree cutoff to low numbers, and then I would get a lot of relationships in my graph. And the same I can do for PageRank, for instance, which also for these small clusters doesn't make so much sense. Um, but sorry, stats. Or probably we can call PageRank stream. So we see kind of what is the rank of these nodes that are in here. So yield node ID, comma score, order by score descending, limit, let's say 20. Oops. So we see that some nodes have a really higher PageRank in their clusters than others. So what we could do now is to say we want to write this back to the nodes and say write property is PageRank, and it has of course different yield things. So we just remove this stuff, and this writes back 392 properties. So we have now on our tags, when we look at the tag, these have now PageRank entries, right? Each tag. So for instance, Neo4j has pretty high PageRank in its cluster. Okay. So what we can do now is we can use Bloom. So I just copy here the password for my sandbox and say username is Neo4j and password is this. And then it connects to my graph and infers the perspective, including the computed relationships and properties, right? So the PageRank property and the similar relationship with the with the that's it. The similar relationship, which still doesn't show up. I don't know why. So we can call db schema visualization again, and we should now see that there's actually a similar relationship between tags as well. Right? Okay, so Plume connected to our graph, and we now can create a perspective, generate a perspective for this graph, and use it. And because we have our indexes that I created at the beginning, we can now see certain nodes. For instance, we can find Sam, who is a very prolific answerer. And if I expand this node, then I should see, if I expand this node, I see like all the answers that he has sent out, 246 answers in the last 2 weeks. So what's happening here? No. So my computer is probably again overloaded with OBS and all the other stuff running. So before I had OBS running, it was actually there immediately. Come on, can do it. So I could also find some, of course, here. And there was one trick that I wanted to show you and expand it here as well, right? So that would fetch like all these relationships from them, which you see is quite a bunch. By the way, there was one trick that I wanted to show you before we go into Bloom. Remember how we did before the fetching users by answer counts? So in our current examples, we just fetch the user and the answers, right? So we said user provided an answer, and then we said return u.displayName, count star as frequency order by frequency descending limit 10. So if you profile this query, then we see that it does an expand first, and then a finds all user nodes, expands them to the answers, then filters for the label of the answer, aggregates that, and returns the results. What's a more efficient way of doing that, if you're only interested in the degree, actually, so because that's the degree and along this line, we can just say, what's the size of this pattern here? So from user to provided, from user via provided to a node. And this value, so the degree of the node for a certain relationship and direction, is actually stored with each node. And so we can, instead of doing the expand, it would just read the degree from the node. So if you look at this plan again, it just says scan the nodes and then project and said read the degree here, right, for this direction and this relationship type. So that's a really neat thing to keep in mind. You don't need always to expand and count, but you can oftentimes, if you don't need to filter by the end node label, then you can also use the degrees here. That was something I didn't want to forget to mention, at least. So Bloom has also hopefully recovered now. Let's see. Did it or did it not? Not really. That's really weird. Anyway, what I wanted to show you with Bloom anyway was the following. That we can now actually render our tags and similarity relationships by the properties that we computed. So, okay, let me just kill this tab and open it again. I'm not sure what's wrong here. Sorry. Oh, Twitch is running in the background here. That's probably not so helpful. Okay, clear my scene. So what I wanted to show you is basically for the tags, we can now use rule-based styling. So we can say, okay, we want to style on the PageRank relationship, the size. So we can say, okay, the min PageRank is 0 and the max PageRank is, I think, 2. And this should kind of be size 4. And we can do the same for, by the way, we can also give tags an icon, of course, and say that's a tag. And the user gets an user icon, and in question gets an question icon. So, and then relationships, we can also take the similar relationship here and add rule-based styles for the weight property that came out of our computation. And we can say, okay, we want to do a color range, for instance, the darker from 0, or it actually starts at 0.2, as that was our limit. And then we have 0.8 here, for instance, and 1 for color. And for size, we also say 0.2 is our, let's say 0.5 size, and then 1, which is the maximum for similarity is 2x, for instance. Okay, and we want to apply these to, and then if we find tags, I hope this works now. So it found 400 nodes as a tag, and should actually render them of different sizes based on their page rank. Let's see if that. Oh, I didn't apply this style, I think, for tag. Rule-based apply size. Apply. Click. So you see that some of the tags are actually now bigger than others here. Why is it not showing the names of the tags? So tag has actually a name, and it should be used as caption. Yeah, okay. Perhaps it's just not done rendering, which is really embarrassing because it's actually usually super fast, but with OBS in the background, it's not as fast. So, and what I wanted to do now is basically select all. So Command A, does this select all? Yeah. So select all and expand the similar relationships. Expand. And we want to expand all the similar relationships here. And hopefully it should, you see it starts to render them in different colors and sizes as such. But I really need to figure out how to get a better setup for the OBS and Bloom at the same time. So like two WebGL users at the same time doesn't seem to like each other. Anyway, that's what I wanted to show you actually, is kind of how you can then take the results from the graph algorithms and visualize them, for instance, in Bloom. And then what's actually quite cool about now that I have the similarity graph, I can now use that, for instance, to recommend questions to answer. So for instance, if I have a user who answered certain or provided certain answers to certain questions, provided answers to a certain question. So for instance, where u.display name is, let me just kill this tab here. Where u.display name is, what was this, the teacher? Let's just see. So he provided, they provided an answer which answers a question, which is tagged with a certain tag. But this tag also is similar to other tags, basically, which are tagging another question. For instance, s.weight is greater than let's say 0.5. Then we can say, okay, which other questions should this user also answer, right? So we say q2.title, and then we say how frequently these questions pop up. So because multiple tags can have multiple similarity relationships, so we can count the frequency, or we could count it and or sum the weights, for instance. That would also be an option. So we could say sum.s.weight. Then that's kind of how frequently and how strongly these are similar, basically. And this would give us, for this person, a set of alternative questions that they could answer as well. And we don't get any. Let's see, CyberSam. Perhaps our weight is here too high. Our weight limit. User provided answer, which answers the question, which is tagged with a tag, which is the wrong direction here. That's why. So let's see. So we see, for instance, OGM things. We could even collect the text that were used for this. Let's see. That's frequency. Collect distinct t dot name plus collect distinct st1 and then st2. So we see also which kind of sets of tags were kind of used for this recommendation as such. Right. So we can so you see that he answered already things with these questions, and then with these tags, and then those others are kind of inferred for that. So it's basically the same here, but in a real world scenario, that would also show other tags as well. Right. So that's something where we can then use our computed similarity relationships that enrich the graph for new kind of questions that we can answer as such. And that's about it.